Okay, we're going to talk about energy for a little bit here. Bond energies and bond length. So we can use individual bond energies to estimate heats of reaction, enthalpy changes of a reaction. So then, of course, we have to define what's the bond energy. Bond energy is the energy required to break 1 mole of that bond in a gas phase, These are always positive. It always requires energy to be put into the molecule to break it. And that should make sense. A stronger bond requires more energy to break. So we can write an equation for that. Here we've got hydrogen chloride in the gas phase, and we put energy into it. We can break it into hydrogen atoms and chlorine atoms. And that reaction has an enthalpy change of 431 kilojoules for every mole. So each molecule has 1 bond, so a mole of molecules are breaking a mole of those bonds, 431 kilojoules. Compounds that have strong bonds tend to be more stable and less reactive. And it kind of makes sense. You know, you've got a Lego structure that's really firmly put together, right? It's got it's not just one of those little tiny things that are sticking on barely. It's going to be stronger when the pieces are glued together, right? So, of course, bond strengths are going to be a little different in different compounds. So like a carbon-hydrogen bond, the amount of energy needed to break it is going to depend on what compound we're talking about. So we look at tables of average bond energies. So if we're looking at the carbon-hydrogen bond, if we've got methane and we're going to break off one of these hydrogens, 438 kilojoules. If we've got trifluoromethane, it's going to be 446. Tribromo, it's 402. Trichloro, 401. So the presence of different atoms in the rest of this molecule affects the strength of the carbon-hydrogen bond. So we're not going to worry about individual ones. We're going to look at an average. But it's important to understand that these delta H's are averages, and so they're more estimates. If you have double and triple bonds, they're going to have higher bond energies than single bonds. So here's a table from your textbook showing average bond energies. So, here's carbon bonds. There's a single bond, 47, a double bond, 611, and a triple bond is 837. Now, the triple bond is not 3 times as strong as the single bond, but it's definitely stronger. So the more bonds there are between the same 2 atoms, double, triple, the stronger it becomes. There's one exception in here we have to watch out for, and that's this carbon-oxygen double bond. There's an asterisk here. And down here it says, but it's 799 in carbon dioxide. So the average is 736, but if you're doing carbon dioxide, then you want to use 799. And so we just go and we look these up. So we can estimate the enthalpy change of a reaction by, again, imagining that we're taking this apart, we're taking our reactants apart, and then we're putting them back together. And we could look at, well, I just need to break this one bond and this other bond, and I'm only making this bond. And so we could be really selective like that and just look at the actual bonds that are broken and the bonds that are formed. But that requires more understanding and is a lot more thinking. And so I think it's better to just go all out and say, I'm going to take all the things apart into atoms. How much is that going to cost in energy? And then I'm going to put them all back together to make the products, and we're going to remake all those bonds and look at what I get back. So we're looking at the sum of the bonds that are broken. That's a positive number. And the sum of the energy from the bonds that are formed. And that's going to be a negative number.